Hi everyone. So I'm taking you back to La Palma, and my name is Ana. I'm from a PhD from the University of Manchester, and we spent some time in La Palma, a lot taking measurements with FTIR. So I'm gonna show you some of the results. So first of all, yes, so we know where the Palma is located, and trust me, some people don't know. Some people put the eruption actually mainland. During the eruption, suddenly we have a volcano in the middle of Spain. So La Palma is located near Africa and is part of the Canary Islands. And the Canary Islands are formed by 7 islands. And this one is Tenerife. Most of you may know because it's a tourist spot. And then La Palma is located west, right here. So there has been 8 historical eruptions in La Palma. The latest one are Teneguía in the south that you heard this morning, 1971, and then San Juan, which was located actually quite near to the 2021 eruption. So it has 2 lava flows, one here and the other one here. And an interesting fact that some of you may know is all the eruptions in the Cumbre Vieja ridge actually end with a big bang. So it has a big explosion on the last day, and then it just keep degassing. So that's what happened also during Tajogaite eruption. It started the 19th of September at around 3:10 local time with a fissure opening, and then it rapidly evolved into a cone-shaped eruption. So the eruptive style was mainly strombolian, and the division of the activity was kind of the same during the eruption. So we have a front bend with lava flows and effusive spattering eruption, and then the top bends we have explosive activity and pyroclastic emission. So this is just some examples of the activity that we saw during the eruption and how the cone evolved and changed at different dates. So the motivation, I think, is quite clear. This was the first eruption in the Canary Islands in 50 years sub-aerial. And then, well, it was the first one that actually has some monitoring done in La Palma, a lot of monitoring because there was a lot of people there working. And someone asked yesterday if there were someone looking at the degassing. We are. And the plume composition actually can provide the depth of the magma. So, sorry, we went there the beginning of October, about 2 weeks after the eruption started. We took our open path Fourier transform spectrometer, which you see in the image. It's a MIDAC spectrometer for those interested. And then we stayed there throughout the eruption. So we took pretty much daily measurements of the eruption from different points in the island around the cone, depending on the lava flows, visibility, and also in the security. So what we did, we measured the chemical composition of the degassing using absorption spectra of the radiation. So, to do so, you can use 2 different geometries. The one on the top, the one here, you basically point the instruments towards the lava body or the incandescent ash, and then you use the radiation to acquire your spectra. The one in the bottom is passive. So basically, you use the sun as you install your instrument between the plume, the sun, and then you are in between. No, sorry, FTIR, plume, sun. So you get the radiation, but we won't be talking about that. Today we will focus on the direct measurements. And then one advance of the OP-FTIR is that you can process the data on the field because you have your laptop connected to the instrument, and these are the wavelengths that we use to retrieve the gases. So we will be looking at 3 different gases, and we have paired them in 2 ratios: SO2 HCl on this one, and CO2 SO2 on this one. And also we have plotted the volcanic tremor with an amplitude of 1 to 5 Hertz. Nanometers per second, and then you can see there's a lot of variability throughout the eruption. So we are going to be looking at it in bits. So first, we're going to focus on the first couple of weeks, we have really low ratios in both ratios. So what we did during this period is we installed our instrument pointing towards the effusive spattering bend, and this was because the geometry of the volcanic edifice allow us to see the lava coming out pretty much. So we installed our instrument here, and we measured the radiation coming from this bend. Also, the sketch is more representative towards the middle end of the eruption, but I didn't have time to draw another one. And what we saw during this period is like a major influence of the soluble volatiles, the chloride and the sulfur. So that's why we have low ratios of CO2, SO2, SO2, HCl. Then there was a change a little bit on the eruption style. There was an increase on ash emission. We didn't have access anymore to the previous position because the lava flows moved forward, so we couldn't not point the instrument anymore to the effusive spattering bend. So we found another places to measure, and we pointed our instrument to the explosive activity, which was mainly lava fountains. So these two. And what we saw here was the opposite. We saw an increase in the ratios of CO2, SO2, but also in the SO2 HCl. And the lava fountains resemble a lot the activity of the stromboli. However, these one were constant, while stromboli lava fountains are intermittent. And we think this is because the branching that took place deep, where you have soluble gases going towards the effusive, and more less soluble gases such as SO2 going toward the explosive bend, being able to form larger bubbles that originate the lava fountaining. And here is the data. And you see some variability besides the high points, the peaks that we measure, like, for example, in this or this. And this is also due because winds are quite changeable in La Palma. And sometimes we will see 3 clear plumes, but other times the plume from the front bend will drift backwards. So we will measure in actually the influence of the front bend instead of the ones for the explosive. Something to remark is we measure, to our knowledge, some of the higher ratios of CO2, SO2 in La Palma, and this is a clear example of the conditions that we measured. This was about 500 meters from the bend, and nothing in between, no influence from the back bend, and we recorded a ratio of 52. Then we have the bit on the middle from the SO2 HCl, where we see a really low ratios, and we think this is due to the solubility of the chloride, and because there was a higher emission of ash, this promoted the emission of HCl, and we recorded really low ratios again of SO2 HCl. And to conclude, basically what we saw in La Palma is different bends have different gas emissions. So we have fractional magma degassing with higher CO2, SO2 measured in the explosive bends, while the smaller ratios of SO2 HCl were measured in the effusive bends. Then we see a high influence of fragmentation on the during large periods of, during periods of high pyroclast emission, and then towards the eruption we see more the true explosive nature of the eruption. And then, to our knowledge, these are some of the higher CO2 SO2 ratios measured with the FTIR during an eruption. Thank you.